Thank you guys for coming. We're very excited about this conference. And when the planning committee got together late last spring to start thinking about what we wanted to do, we started thinking about who we knew that was doing innovative research on education, teaching, and learning. And we came up with a list of faculty from around the country that were really doing this. And we were very excited about the positive response to our invitations to attend this conference from our speakers. And the first speaker is really one of the people that really exemplifies the innovation and in this field of education and innovative thinking about how we should approach education in STEM fields. So Wendy Newstetter has a very unusual background for a faculty member in engineering. She is currently a biomedical engineering faculty member at Georgia Tech and Emory University, where she studies the science of human learning and develops engineering curriculum based on these research outcomes. Her background is she has a BS degree in Asian Studies from Colby College, and then she went to Lancaster University for her master's and PhD in linguistics and cognitive science. So at Georgia Tech, she's worked in a variety of different fields. She's been in the School of Literature, Communication and Culture, the College of Computing, and is currently in biomedical engineering. So she's really going to kick off this session with a discussion of why she's doing what she's doing and how the U.S. really needs to address the changing needs in the field of science, engineering, math, and technology. So with that, I'd like to welcome Wendy Newstetter.
I actually call myself an embedded cognitive scientist. I've embedded in a lot of communities. So I'm really honored to be here to be part of this wonderful set of 2 days where you set aside time to think about what should we be doing in our science, technology, engineering, and mathematics classrooms. It's the second time that Bob and I have been a tag team at a conference, and I think we are well suited as a couple because we are both concerned with the design of optimal learning environments. And when I say the design of optimal learning environments, I'm not talking about content per se. I'm talking about the deployment of spaces, the design of spaces, how spaces actually impact the possibility for learning, how spaces impact the possibility for activity, and how activity in the classroom impacts the possibility for what could be learned. So Bob's going to be talking very specifically about classrooms, and I'm going to be talking about a 6-year research endeavor that we have been engaged in at Georgia Tech, trying to look at authentic sites of science and work and figure out ways to translate what we're finding there into designs for classrooms. And I'm calling this a translational model of research and development in STEM education. And I would imagine that many of you in the audience would consider yourself doing translational research in the context of science or engineering. So I want to visit that paradigm, and then I want to actually explain how we are applying it in the context of STEM education. So in traditional translational research, you have a laboratory setting, you have a bench top where knowledge is being made, original knowledge, novel understandings. So we have a traditional classroom where novel, original research is going on that is interesting to the person in the laboratory who may not be particularly interested in getting it out into the world. And there's this very well-known phenomena that many people refer to as the valley of death, that a novel idea gets stuck in a laboratory and actually never gets transformed into a clinical setting, an industrial setting. So there are a lot of efforts to actually bring laboratory work out of the laboratory and into applications that might be available to people in the real world. So you might consider the laboratory in some senses is a very synthetic environment. It's very constrained, it's very designed, shall we say, to actually address very, very specific and constrained questions, which is in contrast to the authentic environment of the clinic, the industry, wherever this knowledge might end up. And this is the typical notion of translational research. Now, we've been operating with a slightly revised understanding of translational research. In our model, the actual authentic site would be the laboratory, the research laboratory, or industry, that we might refer to as the in vivo setting for authentic, in the wild learning. It's not scripted, it happens on the benchtops, it happens in offices, it happens on the industrial floor. And no one prescribes or tells people how to learn or decides how people will learn. It's authentic, it's in the wild. Now that's where we would like to find design principles for designing classrooms, which are in fact synthetic environments. They're designed, they're highly constrained. This is a very highly constrained synthetic environment in a sense. And in a sense, it's an in vitro environment. And I would suspect that many people would say, well, we're trying to do that. We're trying to make the classroom relevant to the world outside the classroom. But I think in many ways you're delusional. This does not look like a laboratory. This does not look like an office building where people actually do work. This is a contrived setting that actually says there should be a spectacle going on right up down here at the front. It's more like a movie theater, if you think about it, okay? It's not about actually engaging people. So we are trying to figure out how do we take what is going on in these authentic sites and translate them into models of education. So even more so, let me take it further. I want to actually begin to think about merging these authentic sites of science and learning with the classroom sites. And so what that would mean, if we could do this well, is this big division between, well, there's my research and then I have to go to class. This division between the endeavors of doing research and your classroom duties. And how often do you hear people say that, oh, I've got to go teach, I'd rather be in my laboratory? Well, it's very simple, because they're really excited by their laboratory work. They want to be in the laboratory, or they want to be working with their grad students, because that's where the excitement is. The excitement is not in doing problems in the back of the chapter in the textbook. That's boring. It's boring to the faculty member. And frankly, I think more and more for these millennials, it's boring to them. So I said to Bob, geez, there's a great area back up there for Facebook to be going on, because that's what's going on in classrooms. There's a battle going on these days between the millennials who have their laptops, and they are not engaged with the lecturing format because they have access 24/7 to all kinds of information, and they are in the back of the room doing Facebook or Twitter or a lot of other things. And it's a problem. It's a problem that we have to acknowledge, and we can do things like turn off the Wi-Fi in the lecture hall. I've heard of people doing that. Or you can face it. You can face the problem of our pedagogies aren't relevant to the millennials anymore. And it's really beginning to potentially threaten the whole enterprise of the university if we don't begin to think about this seriously. But there's another thing I want to actually suggest. If we begin to bring the laboratory and the classroom together, bring greater parity between the two, then it's possible that we have influences going both ways. And I'm going to hopefully talk about this a little bit. That if the lab environment can influence the classroom, it's possible that there are experiences in the classroom that will make the laboratory better, that will make people better PIs, that will make people better researchers. They don't have to be separated. So I think there's a potential for a student and faculty development model. Now, I saw this quote on the plane today. I really like it. Problems become problems when there is a felt need or difficulty that propels one towards a resolution. Students aren't in environments most of the time when they're feeling a felt need. They're just doing tasks that you assign to them. You have to figure out ways to engage students in a felt need so that they feel like they're working towards some kind of problem resolution. So what do we do to try to rectify this? We decided we were going to go and study labs that are conducting interdisciplinary work. We were very interested as cognitive scientists in this issue of what is interdisciplinary cognition? What happens when you bring the engineering skill set together with the biosciences? How does one integrate? What does problem solving look like? Because in many ways, the epistemologies of these two sets of disciplines are oppositional. One likes to idealize and simplify the world, and one likes complexity and description. In some ways, they don't fit together very well, if you think about it. So we decided to go and find out what happens here. So we identified 3 research labs. We studied each of them for 2 years. The first was a tissue engineering lab that is engaged with designing and developing vascular tissue. The PI is extremely senior, one of the luminaries in bioengineering, had been in the field 30 years. The neuroengineering lab, in contrast, had a brand new PI, just started his lab. He was very interested in the question of learning at the meso level, not at the single neuron, not at the brain, but how do we set up a meso-level brain and then collect data on it and then give that brain a body and figure out what learning looks like from the point of view of signaling, electrical signaling. The third lab, we decided to move out of the bioengineering configuration into computation and biology. So we chose that one very carefully because we wanted to try a different field. Now, these were the questions we were engaged with over this time. What is the nature of reasoning and problem solving in authentic interdisciplinary learning environments? What are the kinds of tools, the discourses, the activities, the representations that are utilized, that are foundational to interdisciplinary work? And what does learning look like in these environments? What are the challenges? What kind of support is there for developing skills? What kind of expertise do students need? How do they garner? How do they grab the expertise? In other words, we were really interested in the ecological features of a robust and vibrant learning community. What sustains learning in these places? Because all of you know that the typical learning scenario in any research lab is you have a newcomer. It could be an undergraduate, it could be a grad student, it could be a postdoc. And they have to suddenly enter this community, and in many cases, they may be in a lab that is engaged in work that's orthogonal to what they do. It's not necessarily their area. We saw this time and time again. And they frankly have to start from scratch, and they have to actually learn very quickly on the ground. So we were interested, how does this happen? What supports it? What does it look like? So we used a mixed methods approach. We conducted ethnographic work, and I'm glad there is an anthropologist in the front row. At least there's one social scientist here. For those of you that don't know what ethnography is, it's the methodology used by anthropologists. So imagine the vascular tissue lab is an exotic tribe with rituals and very strange ways of doing things, interpretive procedures, artifacts that we go in and we study through participant observation. We collect artifacts. We do a lot of interviewing.
So to get very specific, we looked at the physical spaces in the lab. We attended reams and reams of lab meetings and audio and videotaped them. We attended journal clubs. We went on lab tours. We were in mentoring sessions. We attended PhD proposals and defenses. And we looked at all members. We looked at the undergrads, the graduate students, the postdocs, the PIs. In addition to that, we did something called cognitive historical analysis, which is trying to follow the intellectual cognitive trajectory of a lab over time by looking at the lab at a point in time and then tracing the changes that went on in terms of the kinds of questions that were asked, the artifacts that would build, how a particular artifact might actually scaffold the ability to move on to the next aspect. So biographical cognitive trajectories in these labs. So we tried to look at that as well. So very briefly, outcomes. 235 interviews, audio tapes, a 59 research meetings, reams and reams of field notes and conference papers, tons and tons of data. Now, outcome. We have some pretty interesting cognitive descriptions of the practices in these labs. We also have good descriptions of the ecological features that actually support the robust learning. And if you're interested in this and want to find out more, we just had a book published recently by Cambridge University Press called Science's Psychology, Identity and Sense-Making in Science Practice. So what this really means is we said, if we want to understand human psychology, where better to go than a laboratory? Where better to go than the frontiers of science and find out, what does problem solving look like there? What does emotion look like? What does learning look like? What do gendered practices look like? So that's where we have a lot of this. But today I want to talk about the learning. So these are the very specific design principles that we extracted, and they're very high level from these labs and have become what we call design principles for our classrooms. First, and very obviously, what drives learning in the research labs are complex, non-routine, cross-disciplinary, open-ended problems for exploration. What gets people up in the morning and into those labs are these problems. And they can be very, very local problems, like we got a new piece of optical equipment and no one knows how to use it. Who's going to figure that out? Could be something really significant. Our cell line died. It keeps dying. It's 4 months, we can't get any of our cells to live. What are we going to do about that? Or it could be very complicated questions about, we need to build an in vitro environment that will allow us to test the forces that our vascular construct will undergo in the context of the human body. These are all problems to be solved. And problems are what drive the learning in these environments. For every single member, whether it be the undergraduate, the postdoc, the PI, or the grad student. These labs are very agentive. Okay? By agentive, we mean that the learner, the lab member, is an agent, their own agent, in forming numerous relationships with people, with lab resources, with technological artifacts. As agents, they are self-motivated and they are self-monitoring. No one tells them, go learn this necessarily, or tries to motivate them. And they are also willing to acquire new skills and information as related to the work they are doing at that moment. Relational. We found, we didn't expect this, maybe because we're cognitive scientists, we're always interested in the cognitive apparatus, but that really one of the very important foundations of learning in these labs is forming multiple relationships with other people. Interactional structures that allow for rapid participation and membership in a distributed cognitive system, And this motivates learning. So let me give you an example of something that happened a couple times in 2 labs. In one lab, for their journal club, they had a ritual of when they would walk in, everyone would put their name in a hat. And they'd shake it up and they'd pull someone's name out, and that person had to lead the discussion on the journal article that day. Well, one of the undergraduates who was attending their journal club for the first time, his name was pulled out of the hat and was tasked with leading the journal club discussion that day. And as the student said later on, I barely understood the article and I did my best, but it was okay because when I couldn't talk anymore, they just picked up and went on. So this very interesting structure of valuing a brand new lab member to the extent that they would be allowed to try and lead a discussion was very, very interesting. Now, another thing that's really critically important, when you're on the frontiers of science, there's way more failure than there is success. There are way more impasses and more problems to be solved than there is victory. And without relationships, it's extremely bleak. Without the knowledge that everyone else in that room is suffering from failure of various kinds and impasses, and that's part of the culture of participating on the frontiers of science, you need these relationships to keep going. So let me ask you a question about your classrooms. Could you say this about your classroom right now? That it is problem-driven, that is focused on making students agents of their own learning? Do you care about them forming relationships? This was surprising to us. We would have expected in a laboratory with people with extensive knowledge and those with little knowledge that there would be rigid hierarchies. But we didn't find this at all, at least in the labs that we studied. We found that actually the nature of the problems were so vast that there was much more of a vertical kind of stratification. There were points where people were certain experts in certain kinds of things, and people would go to them, but it was possible for an undergrad within 6 months to become an expert in something that no one else knew. And we thought that was really, really interesting, that the enactment of status in these labs was very different than what we thought. The other critical thing is this notion of contribution. What really drives these labs and what really drives learning is the possibility of contributing to a community. So let me give you an example. There was an undergraduate who was in the neuroengineering lab, and he had been doing kind of grunt work. And he had an experiment where he was going to be doing actually imaging of these 10,000 cortical rat neurons, which were going to be sitting on multi-electrode arrays and kind of developing as a brain. And he was going to be the first person to do actually some imaging over periods of time. And this was going to be his contribution to the laboratory. Well, at the very moment that he was about to start his research, they started to have severe difficulty with their cell line. All of the cells kept dying. They had specially genetically engineered cells for this particular work that they were doing. Couldn't get the cells to live. 1 month passes, 2 months pass, 3, 4, 5 months pass, all the cells are dying. So that means they can't do their work. Well, he got so disappointed and discouraged that he actually left the lab. And he left the lab because he felt his one chance to make this contribution had been kind of taken away from him. So this was found over and over again, that what drives people to learn, what drives people is the possibility of contributing to this greater enterprise. Now, if any of you have looked at any of the literature on these millennials, that is one of the hallmarks of millennial students, is the desire to contribute to the greater good, which is really interesting to think about. Adaptability. Obviously, to survive in these labs, you have to be completely adaptable, willing to cope with stress, uncertainty, and then systems thinking. Obviously, in these labs, when you've got problems and you're troubleshooting, the ability to actually harness a systems approach to something rather than a very local approach. And again, I challenge you, these ecological features resonate with anything you're doing in your classrooms? How do you have your classroom set up? What are the status relationships you've set up in the class? Is it strict vertical hierarchy? Is it more democratic? Do you demand adaptability of your students? Do you pull the rug out from under them and make them adapt? Or do you just give them the same old homework assignments? And what are you doing to foster systems thinking? So what I want to move on to is what we've been trying to do is create translation sites, okay? So we've got these high-level principles. How are we going to translate these into models of classrooms? So there's two sites that I will briefly talk about, and tomorrow I'm going to talk, if you're coming to my session, I'm going to talk a lot more about this. One is an introductory methods course. So I call this an introductory methods course because it's a first course in thinking like an engineer. Now, that room where the student is standing and going like this, that is our classroom. So this semester, that class, which is called Problems in Biomedical Engineering, I have 145 students in that class, divided into 17 teams of 8 students. The classroom is a 10 by 10 room with writable walls on all 4 to the ceiling. And every team has a faculty member. I have 14 faculty assigned to one course. They are set up like laboratories, little laboratories. And the faculty member is not teaching, they are facilitating. And this is the class. They meet 3 hours a week in these small rooms. The other translation site is a year-long laboratory sequence where we've tried to retool the instructional laboratory so it's much closer to a research laboratory. So they're not reproducing experiments that someone else did, 25 years ago or 100 years ago. They're trying to do novel work. So to give you a slight flavor of the first introductory methods course, I want to share the problem that my students just are finishing up right now. So my freshmen are doing this problem, okay? Second semester freshmen. The majority of the students have never had statistics, and this problem is heavily imbued with statistics, probability statistics. They have little or no background in cancer biology. They've already forgotten biology. They forgot their biology, okay? You know that. They took it in the fall, but they already forgot it. And they actually didn't learn it. They didn't forget it, they never learned it, okay, which is actually the problem, actually. And so they don't know anything about cancer biology. They certainly don't know anything about cancer screening, and a whole host of other things. This is what in cognitive science we would call an ill-structured complex, ill-constrained problem. Believe it or not, with this problem, we are trying to get them to think like engineers. This is an engineering problem. You may not have recognized that. This is an engineering problem. And the reason it's an engineering problem is we want them to move, by the end of the problem cycle, from reams of studies which they will have found that go down to the level of looking at biomarkers all the way up to using PET scans, the whole gamut of systems in the context of cancer. They will have looked at this. They will be overwhelmed by all the information they've found, at which point, as facilitators, we are going to be trying to move them towards a framework, what we call an analytical framework, that would allow them to actually evaluate and make recommendations. Now, it could be mathematical, because if you think about it, clearly in this problem, sensitivity and specificity are really important, but there are all kinds of other things, and for those of you that are biologists, you know that stage of cancer is huge, particularly in the context of lung cancer, because with lung cancer, beyond stage 1, there's basically 86% of the people die. So you've got to catch it before that. There's the issue of compliance. You might have the best test in the world, but if it's invasive or unpleasant, people aren't going to do it. So we're trying to move them eventually to an analytical framework which would entail metrics of some kind or factors that they could actually apply to a range of screening technologies and come up with both evaluation and assessment. One group actually did a MATLAB, developed a MATLAB script that allowed them to actually run simulations of each one of these that will allow them to look at different mortality rates based on the using one particular kind of test or another. Now, no one told them what to do. You can imagine the amazing number of possibilities for solutions here. So what we do is, at the end of 4 weeks, and by the way, they've only had 4 weeks to do this, they have to present to other teams, and they get to see what other teams are doing. We encourage them at that point to actually look at what other teams have done. If they've done something better, use it. That's what we do as scientists. We don't pretend nothing ever happened before, which is the way most education works. You know, don't imagine anyone else ever did this, you know. But I mean, that's how the science proceeds. You build on each other. One more thing. You might look at that problem, and there are 3 of them in a semester, and if tomorrow I'm going to show the other kinds of problems. Each problem is entirely different. We're doing something that has to do with framing, educational framing. So we're not engaged with single course design. We are engaged with curricular systems design. How do you start an undergraduate experience in a way that allows the learning to go forward, or allows what Nora Surtina in her study of epistemic cultures calls learning reconfigurations? So in the first year in this course, we're going to introduce cancer biology, as you saw in this particular problem. We're going to introduce statistics. We are going to introduce a number of other things, experimental design, modeling. We make no claims that the students have mastered this. They haven't. We don't have an expectation they do. But what we are doing, we are setting the context. We are framing the possibility for future courses. So when they go and take biostatistics next year, and they come to the chapter on probability statistics, they don't need to imagine, why are we learning this? They already know why they're learning it, because they've already done a very significant problem around disease and death and screening. So they know why it's important to understand this probability statistics. So we're creating this environment of what you might call thematic chaining, that you design this first level experience that introduces them to the real world through real world problems. They've engaged the problems. They've not gotten as deep as any of us would go because they only had 4 weeks for each one of these problems. But they have a frame of reference. They have a context. They have an environment for future learning that comes down the road. So later on in the cell physiology course, they're going to revisit cancer, but and they're going to do another kind of problem, which is going to be a much more sophisticated problem they're going to have to solve. But this time, it's going to be either in terms of detecting cancer within the cell or potentially doing cell manipulation for cancer treatment purposes. So the point is, if you're thinking about curricular, if you're really serious about this, I really urge you, don't think single course. Think 4 years. How should your undergraduate experience be set up as a system, a very well thought out and designed system where students have opportunities to continue to revisit topical areas, and every time they revisit it, it gets deeper. So I will stop by sharing my pet peeve. I am so sick of people talking about cover the material. What does cover have to do with learning? Cover means like pulling a sheet over something. And it occurred to me today, because I've said this in many places, coverage from your perspective, and this creates the culture for the students, is task completion. Got through that chapter, got through that chapter, and you know, this goes back to this other battle that's going on in the classroom. We would want our students to learn, and they're doing task completion. But I'm sorry, you're the ones that set up, you created the culture of task completion. When you get so concerned with coverage that it's just you completing the task and them going on with you. So, overall, what are we trying to do? We're trying to frame an undergraduate experience as a collaborative learning in the context of solving authentic complex problems as they would in a laboratory. We are trying to contextualize future learning so we have reconfiguration going on over time rather than coverage. We're trying to shift the responsibility for learning to the students. We're trying to make students agents of their own learning. Not us getting them on our backs and trudging forward. Now, when they become agents, when they feel like they are being tasked with solving very hard problems, it empowers them. And it empowers and motivates them. And it allows them to form a science identity. Because at the end of the day, unless we are engaged in creating contexts where students are allowed to try on a real identity of being a scientist or an engineer, I think we're going to lose them. Because at the end of the day, we are giving them a false epistemology of science and a false epistemology of what it's like to work in STEM. To sit there and have them solve, you know, end of the chapter problems, it says that's what science is or engineering is. That's not what it is. I mean, there's excitement at the frontiers of science. Otherwise, you wouldn't be there. How are you going to make your classrooms closer to that kind of experience? And another thing that has come out of this experience is that all of our faculty members are facilitators in the freshman course. Our senior faculty members with $20 million in grant money are sitting with 8 freshmen facilitating problem solving. As a result, they are now spontaneously changing the way they teach their other classrooms. So we have created what I call an incubator model of faculty development. We can take brand new faculty, we can drop them into this problem-based learning, problem-driven learning, problem-propelled learning environment that's all designed. There's no overhead for them. We come up with problems collaboratively. Frequently, the faculty members will say, hey, there's a really cool thing going on that I saw in the New York Times. Let's turn that into a problem. becomes a problem for our freshmen, and we run that. So we're bringing much closer parity between the research environment and the classroom, but it goes the other way. Because of a lot of the faculty, because they are spending a lot of time mentoring, facilitating freshmen, have told me directly they're better PIs because they're getting better at working as mentors with the grad students. So this is the ideal, to begin to bring these two environments together in a very natural way, and I believe we can do that. So, to be continued tomorrow, 10:30 a.m. breakout session. Thank you very much.
This program is protected by a copyright and may not be redistributed in whole or in part without the express written consent of Rice Digital Media Services.